Thank you very much, Adelaide. So my name is Faisal. I work as a lecturer of water engineering at the University of South Australia, and my country of origin is Bangladesh. I migrated to Australia in 2010. So in the first half of my presentation, probably I will explain the case or the project, which is related to Lower Brownell Creek. And in the second half, I will explain how multi-criteria decision analysis can be applied in water resources planning and management, and I will focus on the case study. So probably many of you know about Lower Brownell Creek. Location, you can see the location in the slide. The length is around 3.3 kilometers, and the modeling of the creek was performed by Tonkin Consulting, and Tonkin Consulting identified that the capacity of the creek is around 25 meter cube per second. But in order to cope with 1 in 100 year rainfall event, or in order to cope with the future climate change projection, the capacity should be upgraded up to 60 meter cube per second. So the problem statement is, how can we upgrade the capacity of the creek from 25 meter cube to 60 meter cube per second, so that it can mitigate the flooding in 1 in 100 year rainfall events. So you can see some photos of the creek, because whenever we took the photo, it was purely dry time, and that's why there is no water in the creek. So in some places the cross section is trapezoidal, in some places the cross section is like a rectangular. And even in the bed materials, in some cases the bed material is concrete, in some cases it is natural earth. You can see the photo of one of our students who basically helped me to do this research. And you can see some of the properties are very close to the creek. That means if you like to increase the dimension of the creek, it could be an issue. And there are significant amount of trees species inside the creek. So if we like to make it concrete, then we need to consider the environmental issue as well. So this is a snapshot of hay-crush modeling. Basically, if you like to measure the capacity of the creek, we can do it based on hay-crush modeling. Or if you like to increase the capacity or increase the dimension of the creek, then what would be the revised capacity? We can usually do these kind of activities through like a hay-crush modeling. So the problem statement is, we need to upgrade the capacity of the creek from 25 meter cube to 60 meter cube. How can we do it? So in order to do that one, we identified 4 alternatives or 4 options. The first option could be like the natural waterway. If we make the creek natural, it will be more environment friendly, but we need to increase the dimensions. And for these options, we estimated what could be the approximate cost, because in Australia we have Rolling Stone Construction Handbook. Any civil engineering or cost we can estimate based on the information given in the Rolling Stone Construction Handbook. And in the second option, we consider if we make the whole creek concrete, then because if we make it concrete, definitely it will increase the flow carrying capacity. And from technical point of view, concrete may be a very good option, but if you make it concrete, all the trees, all the species may die. So from environmental point of view, it could be the worst option. But if we look for the functionality, only the functionality, that is flow carrying capacity, maybe concrete could be a very good option. But best engineering option may not be the best option. The third option we consider we will not touch the creek. The creek will be as it is, because the capacity of the creek is 25 meter cube per second. The next, the additional 35 meter cube per second could be managed by alternate way. So if we can propose box culvert under any road parallel to the creek, that box culvert can carry the additional 35 meter cube per second. So third option is the creek would be as it is, the existing creek. In addition, we'll manage 35 meter cube per second through a box culvert. And the fourth option is similar to third option. In addition, in the third option, we can consider water sensitive urban design technologies, including wetlands. So in order to upgrade the capacity of the creek from 25 meter cube per second to 60 meter cube per second, we basically proposed or designed 4 options. One is the natural creek, one is concrete, one is creek as it is. In addition, there will be box cover, and the 4th option is the option 3 plus water sensitive urban design. Now the multi-criteria comes, which option is the best option? So can we give the ranking of these 4 options? So in order to apply the multi-criteria, we used analytic hierarchy process model, which is developed by Shathi. So under this model, we need to compare the alternatives or options with criteria. So at first, we need to select some criteria. So for this project, we consider 9 criteria, and you can see the criteria are under 3 categories. One criteria is functionality, which is a flow carrying capacity. One criteria is project cost. One criteria is property impacts, etc. And this is the weighting model or the weighting rank. It has been proposed by Shathi, who developed the model, in fact. So the scale is from 1 to 9. So pairwise comparisons of alternative based on criteria could be rated using this scale. So we collected data from 10 engineers who were basically involved in this area, or who knows the project. So you can see the information from one engineer based on only one criteria. So if we forget all other criteria, and if you consider only one criteria, that is the flow carrying capacity, that is the rating scale provided by one engineer. So this rating table, we can form a matrix, and Shathi propose one mathematical approach, and if we apply that mathematical approach, at the end we can produce one normalized matrix. So in the last matrix, you can see the natural waterway has the percentage priority, which is only 4%. That means if we consider only flow carrying capacity, and if you consider the information given by only one engineer, maybe the natural creek would be the worst option. Then from the same engineer, so we collected all the data, and we got the rankings of the alternatives based on 9 criteria. And again, within the 9 criteria, which criteria would be the best criteria? So we need to give the weight of the criteria again. So again, we apply the Shathi's analytic hierarchy process model to give the criteria or weighting of the criteria. And this criteria table, or this information, we can form in 2 matrix, which is this one we call the decision matrix, another one we call the criteria matrix, and if we multiply the matrix at the end, we can get the total weight. So based on the information given by only one engineer, we can see the natural waterway is the best option to upgrade the flow carrying capacity of Lower Brownell Creek from 25 meter cube per second to 60 meter cube per second. And the percentage priority here is 38%. But this is the information from one engineer, but we collected information from 10 engineers. So we consider that the information from the 10 engineers are equally important. We didn't give any weight among the engineers. And at the end, this is the final results. If you combine all the results from 10 engineers, we can see that in order to upgrade the flow carrying capacity of Lower Brownell Creek from 25 to 60 meter cube per second, option 1, which is the natural waterway, is the best option, and the percentage priority is around 29.2%. That's it. Thank you very much.